Alright everyone, so welcome back to my channel. Today we're gonna solve a problem, the earliest moment when everyone became friends. So you have an n people in a social group labeled from 0 to n minus 1. That is clear enough. And you are given an array of logs, which is the timestamp. X and Y will be friend at the timestamp. So friend is symmetric, meaning that if A, for example, if friend 3 is friend with friend 4, right? Then friend 4 is friend with friend 5, for example. Then B is friend with A. Also, so this is meaning is a undirected, so it's not one way, it's two way. Also, a person A is acquired with person B if A is friend with B or A is friend with someone acquired with B. That means that if 3 is friend with 4 and 4 is friend with 5, also 3 is also a friend with a 5. Return the earliest time for which everyone becomes acquired by every other person. If there is no such earliest time, return -1. So for this problem, as you can see, when I draw 3 out and 4, it is a graph kind of problem. You will have friend 1 for this one is 6, right? You have friend 0, 1, 2, 3, 4, and 5. Let's say if 0, 1, 2, 3 right here is friend, right? These are friends and these people are friends. This is, we return -1 because it's two separate component, right? So to solve this kind of problem, since it say that it wants to find on the 1, 2, 3, 4, something like that, we use a data structure called union find. So for this data structure, you have a right union find. You have a log, right? This log is this show the connection between two friends. Let's say friend 1 and friend 2, right? So we add these 1 and 2 into our union find, meaning that we union component 1 and 0 and 1 right here. So union, it will do something like this. So we move 1 right here and we make a connection. So yep, we make a connection like that. So that is called one union, right? If they are union, so that's what happened. So let's say we have something like 1 and 0 right there, it means that it's already a union. So if we have 3 and 4 right here, right? So we have to union 3 and 4, so make a connection right there and something, right? Look like that. So we call it a union. Same thing with the 2 and 3. So we make a union, we make a component that looks like that. So, and then what we can do also is we're gonna sort the log, right? We sort this, so it became, so you know what moment, because we want to return the earliest temp. So we sort this and we go one by one. So what I'm gonna do is, let's say our goal, right? Our goal is to put 0, 1, 2, 3, 4, and 5 in the same component. We will have a union data structure. Of course, we sort the log. So whenever we go through every single log, we also need to have a count right here. Let's say our count, let's say gonna be 6, right? And then we go through every single log and we ask the log, and then we use a union technique, right? We union the two component inside of that log. Let's say 0 and 1. Union 0 and 1, right? If the union return true, meaning that 0 and 1 is combined into one component, we return true. We decrement our count, right? -1 right here. We decrement our count. In other case, when it's returned false, meaning that it is already combined, it's already in a same component. For example, if 0, 1, 2 right here is already a union, right? And then we are asked to we have a log of 2 and 0 right here, it meaning that this is false, so we did not do anything. And then if our count is equal to 1, we return the temp. If we end up the log loop and we did not return the temp, we return -1. So that is all of it, and let's try to code it up, and then I will show you do the union. So let's try to code it up right here. It just simply, first I'm gonna do the log, right? So log sort, right? I have key, which is equal to the x of the 1 of the 0. It means that I just sort based on the first character, which is the temp stamp. I have my union right here, union equal to union of n. And I also have my count, which is equal to n. This is gonna be my count. This is my union data structure that I'm gonna implement later. So for I have temp, friend 1, friend 2, right? In the log, if my union, I will have a function called union. If I try to union two friends together, union together, so f1, f2 right here, then I return the count as 1. This means that if the union is success, so two different components combined to 1, I will decrement our count, right? Until my count is equal to 1, I would return temp. Return 1 right here, it is meaning that I have successfully combined all the friends on the component as one component. So that's why it's reduced to 1, right? Then I return -1. So this is the base code. Now I'm gonna do the union. So if you don't know union data structure, I highly recommend you to look over it and how it's worked. I'm just gonna go through briefly how unions work. So this is just an initialize. I will have myself of parent, right? And the self of rank, right? So this rank is just an extra step. You only just need a parent, but this rank is just an extra step to make the temp complexity better. So for I in range of n, which is 6, we have 6 friends, right? So we have a self.parent.I, which is equal to I, and self.rank I equal to 1. So why we are doing this? We have 1, we have 0, right? 1, 2. For example, we only have 3 friends. Every single friend is gonna be a parent of itself, right? So when we call union, we're just saying that, oh, this one gonna be a parent. Remove this. Let's say we union 0 and 1. It could look like this. 1 is 0 is parent of 1, or we could do something that look like this. So 1 the parent of 0. So this is called it when we know that this is the 1 as a 1 component. So that's why we have that right there. In union, we also need to find a parent of a node. Let's say we have 0 right here. We have to find a parent of it. On the way at the top is 1. So if we call a parent of 2, it is because it's the parent of itself, so it's already the parent of itself. So this is where we need to, this is why we need the parent, right? So let's say we want to union 1 and 0 again, right? So 1, the parent of it is gonna be 0, and 0, the parent of it is also itself, so 0. It meaning that these two have the same parent. It means that, oh, this one is in the same component. That is just the basics. Just how union find work. That's why I write it right there. So I will have to write find function. So find self node. So I have my node right here. So my parent would be equal to the self dot parent of the node, right? So while my parent is not equal to the self dot parent, right? This is when we stop. We're just trying to check if the node is the parent of itself, meaning that 0 right there. Self dot parent p will be equal to the self dot parent is self dot parent of parent right here. So this technique we use to prune the tree. Let's say return p. For example, why I'm having this, let's say I have 0, 1, 2, 3 right here, and 4 right here, whatever. So this is the 0 is a parent of 1, of 2, of 3, right? Let's say we're trying to find 3, the parent of 3. We have to traverse 2, we have to traverse 1, we have to traverse 2, 0 again. This technique is used to ruining that process. If, let's say, we have 2 and 3, right? We have a 2 and a 3 right here. That's how do I remove it? Be right here. Yep. If we have a 2 and a 3 right here, we're trying to union 1 and a 3 right here, right? So what we do is we find the parent of them, right? This is the parent, 0 and 2 is not equal, so we can union them as 1, right? So when we union them, it's just that we're trying to make it like this. Either way, so this code right here, it would try to make it like this. Yep, it would try to make it the lowest possible, or we could do it like this, or it could do whatever like this. But at the end, the parent will be always the root node at 0 right here, right? So it will make the traverse up here shorter, right? And whenever we call 3 again, for example, just 3 again, right? We make it link to the root. So instead of 3 connecting to 2 right here, which we remove this, and then we move the 3 right here. Oh, my bad. So move 3 up here, and we link it to 0 like that. So it make it shorter to find a parent. Just that is the case. So this is why we have that right there. And we definition of the union function. So union also is have self. We have node 1, we have node 2, right? And then in here we have to find our parent, right? Parent 1, parent 2 will be equal to the self dot find and 1 self dot find and 2 right here. So this case is where if the 2 parent is the same, we return false, right? We return false right here in order to run this function. It means that if 2 parent are the same, it's already union. We don't have to union it again. We don't have to run the count -1 right here. We can move forward, right? So that is why. And then if the self dot rank is p1 smaller than self dot rank p2, self dot part p1 equal to p2. So why am I have the ranking right here? Again, it's just used to optimize. You don't even need the rank right here. You just arbitrarily pick P1 and P2. It doesn't matter. But the rank system right here, let's say you have 1, 2, and 3 right here, and you have a 4 and a 5. And this one is 6. Just for example, right? You would like to take if the rank, let's say rank of P1, this one is P1, is smaller than the rank of P2, right? This one is P2, is longer. So our parent of the smaller one would be plugged to P2, right? So we want this 4 and 5. Just look like this, right? Parent of P1 is P2. We want to make it look like this. We don't want it to look like if we do the opposite, 1, 2, 3, 6 right here. This is longer, 1, 2, 3, 4, 5. This 1, 2, 3, 4, right? This is longer. This one is more balanced. So that's why we have a rank system right there to keep to optimize it. You can arbitrarily just add more and more, but using the rank plus the self parent right here, it helps to reduce the time complexity a lot. So that's why I have a rank right here, and leave the other case, right? So the other case, change thing. Self dot parent of P2 would be equal to P1. And in the other case, when they are the same rank, I just pick P1. Doesn't matter. You can pick whatever you want, and then you have to increase the rank of P1, right? Rank of the rank of P2 because it's a parent. So return true right here, meaning that we finally do the union. And then we'll just run through this real quick, see what happened. Oh, something wrong happened. Let's try to figure it out. Oh, silly me. I found my error. This is the one right here. It should be minus equal 1. It's not like that. So let's see. Very good. And it's quite efficient. The time complexity is definitely the log of an O, right? The log. And then we have to initialize this initialize of the n. So definitely n. What we initialize it here, we sort, so it's gonna be log times log of L, right? Because we sort the logs, we have n. And then for a union right here, since we use the optimize right here, we have a parent, we have a rank. It is constant temp. So this is the result right here. The temp complexity, the space, of course, going to be n because we use the union right here. So and thank you for watching, and hope to see you soon on our next video.